Yeah. Hello, welcome. As I said, my name is Fredrik Linder. I have more than 15 years of experience on server-side development, mostly Erlang and C++. I currently work at Machine Zone. I have. Does it work? Better? Better? Okay, good. Um, and I've previously been at Klarna and Ericsson, among other places. I have a master's from Stockholm's University. How many of you have heard about Machine Zone? Can you get a hand raise? A few of those. That's nice. When I joined almost 3 years ago, we were about 40 people in this one building inside Palo Alto. And nowadays we are a multinational company with offices in a couple of countries all around the world. And we would like to think of ourselves as a tech company. And when I say tech company, in our case, that means that we have what we build and get money for. We need to build some technology to make that happen, because as far as we know, there's nothing available for us that would serve that kind of scale that we need. So we're a tech company that build games, and we build primarily free-to-play games on the mobile market. And so there's a difference on the mobile market compared to the PC market, for instance. On the PC market, the devices that you use, they typically have a lot of energy. I mean, they don't run out the batteries, right? They typically have a quite good and stable network connection. And they usually have quite a lot of CPU and graphics computation power. And on the mobile market, those things are not necessarily there. I don't know if any of you remember original Gangster, iMob, and iNight, for instance. They were, at that time that they were big, they were top-grossing games. Our most recent success, which has been on the market for years, like 2 years, I think, is Game of War. So another hand raise. How many of you have played Game of War? So a few. How many of you have heard about Game of War before this? Oh, that's better. So Game of War is the world's largest single world interactive game. And what I mean by that is for everyone who's playing the game, they are in the same world. Typically when game companies in games, they can have a lot of players, but they are typically isolated into smaller worlds, because that's the kind of scale and capacities those companies are capable of producing. In our case, all players are in the same world, even though, come to that. So we have players all over the world. We started out with the testing in New Zealand to see that everything worked fine, and then it moved forward over to Australia and some other countries in that region. You have to root out all the difficulties and stuff. And then we moved over to the big countries like Russia, France, and the US, and Mexico, to see that that was a big launch. And nowadays we're launched worldwide, and we have players in over 40 countries. Last I checked, I think. So, what do you do inside in this game? Well, it's a game of war. And its setting is a medieval fantasy game. So you build your city, you build your army. You have a hero that you want to improve so that he or she will bring benefits to your fighting or to your strength. You have inside your city, you can build your farms or quarries, or a place to build weapons, or to teach how to teach warfare. Yeah, and then with this army that you have, you can either attack other people or defend when they are attacking you. But you can also go out on the nearby place in the map to gather resources. So going back to technology now. So one of those things that the Game of War needs is a map, and well, this is not the graphics of the map, of course, but it's showing how the map is built. So in our case, the map is built of a large grid of tiles, and a set of those tiles is part of a kingdom. And all these kingdoms share the same, is on the same world. Within a kingdom, we can have cities placed out on the map, different places, and we have resources and monsters roaming around over there. Yeah. So going back to more things about the game. So one of the things that you start off doing in the beginning is to typically join an alliance to get some friends to protect you, to teach you how to play, or to send you resources, help out when you're in trouble. And when you grow in this game, you get more and more involved and learn how to do this better and better. Maybe you can climb up on those hierarchies, or maybe you can create start your own alliance to be the king of that alliance or the leader. And another thing that you do in this game is that you meet people. I think it took half a year or something for the first marriage to happen in the game. With two people who had met by playing this game would get married. So it's typically a social game, right? It's a war game, but the main thing here is that it's a social game. We have these people all over the world playing against each other, teaming up or teaming against each other, and they need some way of communicating because not everybody here speaks the same language, right? So, and one of the things that we need in all this is a way to break that language barrier. And we come back to technology again. So Game of War needs to chat with real-time translations. And yeah, you could think that translation would be an easy thing. You just send it to Google or Bing or something. But those translation systems are based on text with larger volumes, like a book or an essay or something. So the language detection there or the translation things there are based on that they have a lot of information about the text that you're sending. In a chat, you typically have a few words. So you need to be able to detect the language just using 3 or 4 words, which is a very difficult task. And you need to know the language that you're translating from in order to speed it up, because we also do things like chat speak, like LOL or MDR, which is LOL in French, for instance. And we make sure that those things are also translated to the equivalent thing on the language that you are speaking, or that your device is set on, typically. And all this since it's a chat, this translation has to happen in real time, right? You can't have a chat with, you send something and then the other person receives that after 3 seconds. That wouldn't do. That wouldn't feel natural when you play this. So you have to have enough performance in this and enough scale to handle these low latency translations. So I'm not going to go into how we did the translation thing, but I am going to talk about something else later on. So you could say that our company is like in 2 parts. One part is doing the game, figuring out how the game should work, how the art should be, how the interaction should be, how to make people want to stay in the game, want to play more, how to make them want to win things. And then you have the tech side to enable these things. So for instance, there's the map service, there's chat service, translation service, and we have a couple of other ones as well. So that would be on the tech side. So all these things on the tech side, we can reuse them in other products if we want to. And today I'm going to primarily focus on the map service and the chat service. So to be to be honest with you, we don't have a map service. The game, what I call a map service, is actually split in two parts. One part is how the game uses the technology that we provide. Another thing is it's a pub sub service. And chat is also a pub sub service. Okay, now another hand raise. How many knows about pub sub? Almost everybody. That's good. So pub sub was defined, I think, like 20 years ago or something, or maybe 30. And but it hasn't. Since about half of you know about it, it's not been that widespread, I guess. So pub sub is typically you have one or more publisher that sends things over from a topic or a channel or a chat room, for instance. And then you have 0 or more subscribers that get all of those events. And in so the chat service that we currently have, the pub sub service that we currently have, it's fast enough so that when you scroll the map or do the chat, there's no lag. You don't experience that you scroll and then you have to reload the page or things like that. So how does the game people make a map out of a pub sub service? Remember I said that the map was a grid system? So more or less every grid in this system, every square in this is a separate channel that you post events to. So for instance, if you are on the position 3-3, you would see on your map you would see the things around you. Maybe it's like 1-1 to 3-3, the green area. That means you are subscribed to events that happen on those channels. And then you send your army or you scroll around, which means you move around on the map, right? So now you're interested in the other 9 tiles around you, closest to you. So then, since this is a mobile device, we don't want to stay connected to events that we don't no longer need to know anything about, because that would do two things. It would eat up some of the bandwidth, and it would also eat up some of the battery in the device. And we don't want that, because we want you to be able to play for a long time, right? And we want you to not spend your money on the mobile operator. So we need to subscribe and unsubscribe to these channels. So you subscribe to the blue ones and you unsubscribe from the red ones. And this subscription and unsubscription needs to be pretty fast, so that when you scroll, if you continue scrolling, you should, when you go another square up, you should be able to do that in real time. So you will still get all those notifications that you are interested in, and you can cancel the other ones. And in any case, yes. So that's how we map, how the map is implemented using PubSub. For the chat system, it's kind of natively understood, I guess. Each chat room would be a separate topic or channel that you subscribe to or publish to. So in our case, we have each kingdom is automatically. Whenever you start up the game, you are joined in one chat, and that's the kingdom chat. So you can see what everyone says around you in the kingdom. And when you join an alliance, you have access to that alliance chat. But then we also have, you can send one-on-one chats if you want to, or you can have discussions with other people in the game that are not related to any alliance or anything. So that means you can have more or less all kind of sizes of chat system chat rooms. Yeah. So I'm talking about this when you scrolling and there's no lag. That means that there's low latency on all these things. And the latency is typically sub-second latency, or some even better than that. And apparently there's in Japan, there's this there's an underground movement that when a certain popular show is aired on the TV, everybody who's watching that is sending a tweet at exactly the same time during that episode. And for the first couple of times that happened, Twitter went down. And after a while, after a couple of times, they were like, "Yay, we survived it!" One of those bursts. If I have understood it right, we are having that peak capacity every day. But we have a game team who wants to invent new things, right? So they have figured out that this pub sub is a really cool thing, and they want to have more features based on it. And our current system cannot handle all of those things. So we need to improve. And they come back and say, okay, how much do you want us to improve? Is it like 10x or 100x, or is it 1000x? So basically, if there's a 10x, that means that they can select the top priority features and implement them and see that would happen. And to get 10x, you could probably just start up a couple of new clusters, right? So reaching 100x, that would probably not be economical anymore. And with 100x, you could probably get all of those features that they are thinking about. And with 1000x, we could get all those things that I haven't thought of yet, but probably will eventually. So our question was, how fast can we make it? What is the theoretical limit? Well, the theoretical limit would be you check on the network connections and see how big they are and chunk off the size and say, okay, this can be the rate, right? So say that you have 1 megabit, 10 megabit network, for instance, and the typical payload would be 100 bytes. That means quite a lot of messages per second. And then you need to have the system to actually handle it and be to be able to perform a pub sub at that speed. And yeah, that would be great if we could do that. So when it comes to performance, what you typically talk about is throughput and latency. There's a cost of operation as well, but that one also boils down to throughput and latency. Because if you are able to maximize your network usage, and you're having that with low enough latency for the game to accept, you could have fewer less hardware, right? So that boils down to throughput and latency. So how many of you have heard about Little's Law? A few of you. Okay, that's good. So Little's Law is it says that on a stable system, the average throughput of that system equals the average number of messages that is in the system divided by the queuing delay imposed on those messages. So what does that mean? So number of messages, that's one thing, right? So okay, I take that less soon. And latency, the time experience from the client side, is the sum of two things. It's the processing time for those events, plus the queuing delay that is imposed by the system. So naturally, we want to maximize the number of messages in the system and minimize the queuing delay, and also minimize the processing times. And there are some techniques that you typically can do to meet that. To maximize number of messages, what you typically do is, or there are two things. You can do things in parallel, but that would scale only up to number of cores, because after number of cores, you would induce. That's the only thing you can do at one time. So what you would do is, if you add more things in parallel, that means you'd add queuing delay. So in our case, with the PubSub system, we have an ordering guarantees as well. For instance, if you send a message to me, I'm supposed to receive those in the order that you sent them, just as in Erlang. So in Erlang, I think that the delivery is also guaranteed as long as nothing fails and crashes and stuff. But in our system, we do not guarantee that, because that's a little bit too costly for us. Instead, we make sure that any messages that you send, if it is acknowledged by us, saying that, yeah, we have received it, then it will eventually be sent. If it's not acknowledged, that means it might have been sent. You don't know unless you subscribe and see that you get it. The other approach that you would normally take is to batch up messages. You can do this if you can reduce the processing time to handle all these messages. For instance, say that your processing will be a truck. If you can load it with one thing, or we can load it with 10 things or 100 things, that would be the same cost of driving the truck from A to B. Okay. So then minimizing queuing delay. If you look at it on a network perspective, that means that you would ideally be reading in a faster pace than things are written to that TCP buffer. That would mean that whenever you take something out of it, that means that the sender would always be able to send, that's when you reach the high capacity, right? So we are using GenTCP, which I guess most of you have heard of. And GenTCP has it both handles the TCP layer, or VM does, I think, and it also has an internal buffer that you can control that by the buffer argument. That was a killer thing for us. You also need to have some kind of fast enough parsing and dispatching of those messages so that you can read the next chunk before it gets filled up in the TCP buffer. So the TCP is at any fixed time, any specific time, it has a fixed size buffer for reading and writing, and also the buffer in GenTCP. On an process inbox instead, it's not limited by size. You can crash the VM by loading too many messages in an inbox, right? So the ideal there looks a little bit different. So when you ideally, if everything is really, really super fast, so whenever you get scheduled out from the scheduler, so your runtime is up, that means whenever you have done 2,000 reductions, that's when you get scheduled out. Ideally, your inbox should be empty at that time, you should have low enough processing to allow that to happen. And yeah. And another thing you can do, so if you have like 40 cores, for instance, and you have 200 processes, active processes that are doing things, 160 of those would be waiting to forget the execution time. That waiting for execution time is queuing delay. That's how they need to wait to get things done. So to minimize the queuing delay, you should minimize the number of active processes. That does not always map well to the thing that you want to do, right? So for our case, if we have, say, 1,000 or 20,000 connected clients, all of those might be active at the same time, and you can't really do something about it. But it's something to think about. So when you're testing your system, there's one thing you should have a watchful eye for, and that's processes with big, large inboxes. Because if there's a large inbox, that means the queuing delay, the time it takes from that you put that message in the inbox until it has been processed, that's the larger the inbox, the larger the time it takes to get that thing handled, and that means the larger the queuing delay is. And you don't want a large queuing delay when you have a high throughput system. And another thing you should also avoid, that's synchronous blocking calls, because that would, while you're blocked waiting for the reply for something, that means you can't eat anything from your anything else from your inbox. So that in certain situations that doesn't really matter, but for the critical path, that might be crucial. Okay, so the minimized processing time, that's normal, hardcore stuff, right? You figure out the right algorithm, you know the right data structures, you know exactly how many reductions your language constructs take. So one thing that I believe is not that common that you're thinking about is that you shouldn't generate any garbage. Even though the garbage collection is kind of great in Erlang, it still generates data that's not needed in your system. And creating data that's not needed, that's just kind of waste. And if you can get away from it, that would be a great speed up. I will show some example of that later on. Okay, so back to our current and new PubSub. So the current PubSub we use is Jeopardy based. It has a single node type. So whenever you want to scale out, you just add a node. And if I remember right, there's a session table in Mnisa session table that collects, so you can know where all the rooms are. And since it's Mnisa, it means you can't really scale it out in that many nodes. And it also means that all nodes are interconnected. They need to know about each other. And we have an XMPP protocol that is kind of heavy to parse. So in the new PubSub that we have been building, it's everything is built in-house, or the core part of the system is built in-house. It has more than one node type, so that we can optimize certain behavior, and also means we can scale things differently. It typically has an I wasn't really sure how to name this, but like an N-to-M like connection mesh. We have some nodes connecting to another set of nodes, but those nodes internally do not connect to each other. And to make the world a little bit easier on the users of this system, we're using JSON instead of XMPP with a in-house protocol. So JSON isn't like the most efficient protocol out there, but we chose it because that was we can always do better after that, right? So we want to scale more. Okay, so what we did was we split out the multiplexing part of the system. That's the connection, the mapping between the connected clients and the rooms, and the queue, which is where we put all the topics and channels. And we place them in separate nodes, and that means that we can, if we need to add more people, we can just add more MX nodes. And if we need more data traffic, more the volumes of the data become bigger, we can add more queue nodes. And that can be done seamlessly without any affecting anything. Or if one of them die, we can just add another one. The connection would die, of course, but then when they reconnect, that would work again. And when we see that the traffic is shrinking, we can reduce the system and still have a working system, and everything would be great from the cost perspective. Okay, so a very simplistic data path would be like you have a client that is connecting with the socket to connection process, and then whenever someone is posting or subscribing to a certain topic, that would connect to a process on the queue node. So now I'm going to take you by the path to see how to apply those maximize number of messages, minimize queuing delay, or minimize 10 minutes only? Oh, shit. Okay, now I'm going to be fast. Okay, so we connect the client with TCP using Ranch. And we were thinking about should we use active passive mode or active once or active N? So how many think that passive mode would be the best? No one. How many thinks active once would be the best? A few. How many think active N would be the best? That's more. Okay, cool. So I'll skip this. It turns out that active once is actually the fastest. And it also has a nice feature. It has it's a clean way to apply back pressure, which is how we control inflow of data. But this didn't give us good enough throughput. But if you add the buffer thing, which would then maximize the number of messages in the system, so we had like 20,000 as a buffer size, then that would be a good throughput number. I think it's 100,000 or up is actually good. However, if you have a big buffer, that means the queuing delay gets increased. Because the first byte will have to wait for the last byte in order to be handled. So let's have a closer look on the connection process. So one of the problems with the connection process with this simplistic thing is that we get the data flow in two directions are competing under the same inbox and the same processing capacity. And so you need to split it. That means so that then we have two processes, one taking traffic from one direction and the other process taking traffic from the other direction. And they won't be waiting for each other or stealing each other's computation time. It also has the benefit that since it's a network, since it's a mobile phone, you sometimes have the radio shadow. So sending could possibly take over a minute, and that would not block your connection process. So when it comes to message passing, when you go between nodes, we measure that inside a VM, you can do at least 1 million messages a second, typically more. But between two nodes, we could only get 250,000 messages per second. That's Erlang messages, Erlang terms being sent. So the way to measure to address this, since we don't want them to share the same network, we need to buffer them together so that each message, each Erlang message going between nodes contain more of the pub/sub messages that we send. If you look at the queue side, we were trying to maximize number of messages by parallelizing things, and we had an idea that S would be great for this. It turns out that S was actually too slow. So we had to write an if to address this. Then go to the next thing. So let's say when they go from Q to MX. So what we did was initially was when you publish something, you push the message. When you want to subscribe things, you pull in a forever loop to get more messages. However, there are some problems with this. When you push and pull from the same process, that means that they compete over the same resources and same inbox, same as we saw earlier. And another thing when it comes to pull is the topic is unable to send anything while between the pull calls, which would reduce the throughput of the system. And also when the way we designed the pulling is that we said, okay, whenever you pull, you get all the data that's available. That is also bad because that will get an irregular amount of traffic through the system, through the network, and that's bad for performance. And another thing that is also bad is since each individual puller would pull for them unique set of data, a unique range of data, and that adds processing time because you need to figure out where to start and then you can send the rest. So our solution was to create a subscription based instead. So whenever you get data, whenever you push over data, the subscriber would have their own subscription process that would send data to it. So it would have, we push over to the topic process. The topic would then send it to a process that knows where you are, where this guy is on the path, so it wouldn't have to calculate anything. And it can also do this sending in parallel and it can smooth things out. I already talked about limited bandwidth, and to maximize the messages, we buffer them. We don't want to send the same message more than once between two nodes, so we are exploding them on the MX side. However, that also had an issue. See if that's next. Yeah. So, sending messages to a lot of processes takes a little bit of time. How many think it takes? This would take more than 5 milliseconds. Okay, how many think it would take more than 10 milliseconds? Okay, how many more? Okay, so yes, we're sending binaries. No, it doesn't matter. So okay, they're big binaries. So then it doesn't matter. Because if big binary, when you send that within a node, you only send a reference to the binary. So that's pretty small, and it doesn't matter. So it turns out that sending from 1 to 20K messages, the 20K processes take about 80 milliseconds. And it's more or less a straight line for number of the time it takes to send to them and the number of most processes it takes. So that's a good thing, though. So it would be great if this could be optimized, of course. So in our case, we had to write an if to address this. This if is a very special purpose, so it's not something we can share, I think. So, how how much more time do you have? That sounds good. 2 minutes. Oh, right. Okay. So the big part here is, of course, you know that you should find the right algorithm, use the right constructs and data structure stuff. But something that is often not seen or understood is to avoid generate garbage, like I said earlier. So you can like that. So this is a great place to have a look. Efficiency guide. So for instance, in this case, no, let's not take that one. Let's take this one. Okay, I can do it, this part at least. So if you have a fold with that actually creates a list that is thrown away, compared to a for each going over the same list that doesn't create garbage, and you compare that to list comprehension, doing the same thing as the for each loop, there's quite a big of difference in how long time it takes. So choose list comprehensions if you can. So in this case, you have a I'm going to show difference in garbage collection in the cost of garbage. So for list comprehensions, if you have something after the list comprehension and you don't use that value that is returned, the list is never generated, which I think is a great thing. So in the second example, we have the list and we return it, so it means the compiler can't optimize it out, or the preprocessor can't optimize it out. So we measure it, and there's quite a difference. In the test case, I'm not using that list anyway. I just throw it away immediately. So the difference is like 3 times, just because of garbage. That the garbage is built and thrown away. Another thing is you should prefer doing things in line. Sometimes you can't because the sequence of stuff is require you to not do it. But if you can, that's a great thing. So in this case, we're generating garbage by accumulating list in the first step and then doing something new on the second step. And the difference is almost 4 times waste. Another thing you can see is it also has, this is the number of reductions that are used. So when you generate a list and you reiterate on the resulting list, you get more reductions, which is not good for processing time. Okay, I guess I can quit there. Okay. Thank you.
Let's thank Fredrik. And I think we can stretch